All right, this is our last hemoglobin video. And I like to cover this because it's really relevant to human health, but it's also just relevant to biology. And I want to talk now about how organisms adjust to high altitude. Let's think about our standard oxygen saturation curve. What we have said in the past is that the lungs are out here and the muscles are over here, and we're trying to set up a nice big gap over here so that myoglobin wins out in the muscles. That's the essence of this chapter so far. Now, what happens if you go to very high altitude? There's two different scenarios for altitude. I want to start with those that involve organisms at very high altitude, like a llama shown in this picture that has, it lives at maybe 14,000 feet up in the Andes Mountains. Well, in that case, instead of being way out here, maybe the altitude is so high that we end up over here, where the air that a llama takes in is going to be at much less PO2 because they're at such high altitude. Let me ask you, just take a thought here, pause for a moment, and what would you do if you wanted to redesign hemoglobin in some fashion such that it was going to operate better for the llama in the Andes Mountains? Would you change the shape? Would you change the shift? And how would you change it? Pause for a moment, think that through a little bit. Okay, I don't know what you came up with for an answer, but I'll tell you what happens in the llama. The llama has a different hemoglobin than humans have. It's got a few mutations in it. And what happens is the shape does not change, but the llama's hemoglobin is slightly more in the relaxed state, and that makes it higher affinity. And what that does for the llama is it helps out up here. Notice that if it had normal human hemoglobin, like we have down here, the saturation in the lungs would maybe only be at 80%. But by shifting toward the relaxed state and shifting to the left, it means you get a higher saturation. So basically, the problem is in the lungs, and you solve it by making the hemoglobin soak up more oxygen in the lungs. So that's what happens at very high altitude. But what about you? What if you travel to moderate altitude? And by moderate altitude, I'm thinking like Denver or something like that. Let's say you fly to Denver. You're going to go up in the Rockies and hike around at 7,000 or 8,000 feet or something like that. We actually have a slightly different approach. And let's look at the oxygen saturation curve again. We have PO2. And instead of being way out here for lungs, maybe we're going to be here. Not quite so bad. Over here are our muscles. Maybe it's not quite bad. In fact, you can look and see that because there's still quite a bit of oxygen there, we don't really have the problem that the llama has. The hemoglobin is still highly saturated. Maybe it's 98% instead of 99%, but really that's not an issue in the lungs. The problem is that you just get less oxygen overall delivered, and therefore we actually solve the problem in a different fashion. In humans, when you go to high altitude, you have the same hemoglobin, but what happens is you alter the conditions in your red blood cells over maybe 24 to 48 hours. And what happens is we actually do the opposite. You shift to the right. And what that means is it's shifting towards the tense state more than at low altitude. So how does that happen? Well, that's coming later. Why do we do this? Well, take a look. What happens is we actually lose a little bit of our saturation up there in the lungs. Maybe we go from 98% down to 95% or something like that. That's not too bad. But what happens is in the muscles, we actually get extra delivery of oxygen, and the delivery of oxygen is bigger. There's a bigger gap because we've shifted the hemoglobin more to the right, and that gives maybe 15% extra oxygen delivered, even though we're losing a little bit in the lungs. So that is how it works. Human hemoglobin shifts to the 10th state at high altitude. How does that happen? Well, it's a little different. We don't have a different hemoglobin. What we have is a compound called 2,3-BPG. You don't need to know the name of that. It's 2,3-bisphosphoglycerate, but you do need to know 2,3-BPG. And if you look at that structure, what really stands out about it? I mean, what's the predominant chemical principle you see there? I see 5 negative charges, and this is a very, very highly negatively charged protein. Sorry, not a protein, just a compound. And here's what happens. This compound is going to bind to a bunch of positive charges that line the interior of hemoglobin. And let's write this out. 2,3-BPG, when we make more of it, binds in the center cavity. And that center cavity is bigger in the T state, so that stabilizes the T state. And that helps deliver more oxygen because we've shifted to the right. You can see it right there. We've shifted to the right. We end up with a bigger gap, more oxygen dumped into the muscles. After all, that's what you really need when you're hiking at high altitude, is more oxygen in your muscles. You don't really care what's going on in the lungs as long as you're getting a decent saturation out there. So one last note about 2,3-BPG. This happens all the time, even when you're not necessarily at high altitude. In fact, if you have chronic heart disease or emphysema and you're not getting enough oxygen, your body thinks you might as well be at 15,000 feet or 10,000 feet, and it makes more 2,3-BPG, and that helps deliver more oxygen for people with diseases that are hurting them and hurting their ability to get oxygen into their tissues. So it's not just about altitude, it's a common feature of hemoglobin, and it certainly is a pathophysiology issue as well. Okay, I think that's probably enough to cover altitude, and let's finish that video now.